Yes, so we are happy to have Karen Hovhannisyan, one of the founding members of IFS, to give a talk on analog of many-body Berry-Esseen theorem for critical systems. Okay, so he has on his chat. We will not send messages to that chat right now. So, and so I will just tell you what is going to be the time limits. So we start basically past 15. Therefore, it will be around 1 hour. We don't have strict limits. And there will be, maybe, if Karen agrees, some pauses like every 10 minutes where we can ask questions. So in principle, since we are not that many, we can also be more casual, and we don't have to raise hands. We can just unmute and ask questions if needed. Yeah, so Karen is currently at ICTP in Trieste. Please welcome, Karen.
Thank you. Thank you, Karapet. So yes, I would just like to reinstate that you can, in principle, pause me at any time because, well, we're not so many. Maybe Armen will join soon, but well, I mean, we don't know that. So yes, so as Karapet told already, so this is going to be about the many-body Berry-Esseen theorem and its extension to critical systems. So I will try to be introductory, and it will be mixed with slides and handwritten stuff. So let's see how this goes. Well, in case anybody will be curious to read more about the technical details, they are at this archive link. And so yeah, so let me start with a very broad introduction. So imagine like an arbitrary many-body system, right? Let it be a chair. So if you want to know about this system's Hamiltonian, then of course the first question you ask is what is the spectrum of the Hamiltonian of this system, right? As any many-body system which we encounter in our everyday life, it is a short-ranged interacting system, right? The atoms are not interacting with very far atoms that are very far from each other, right? I mean, okay, so only neighbors interact essentially, right? The interaction between further terms can be neglected and stuff like that. So in principle, one can think of a Hamiltonian of a many-body system, of a typical many-body system, as something like this, where you basically have atoms of kind A and B, and they interact in pairs. You know, the eth atom interacts with kth atom of various species, and so this is going to be like the interaction terms, and these are going to be local potentials, right? So this is a typical many-body system. And now, if we ask about the spectrum of this Hamiltonian, we will encounter that it's very complicated. In principle, this is the main general rule that the spectrum of many-body systems, spectra of many-body systems are very complex, and not really much can be said about them in general once given a Hamiltonian, right? And it doesn't even have to be a complex Hamiltonian, right? It can be something very simple like the quantum Ising model that pretty much everybody knows, and the spectrum is going to be fairly complicated. It is so complicated that even the first gap, right? So if this is the ground state and this is the first excited state, the existence of a non-zero spectral gap, right? So even this question can be very hard. It's actually undecidable in the general case. Namely, if you have like an n-body system, you can have up to n equals to n0, where n0 is very large, right? And then the gap shrinks to 0. And in principle, there is no way to decide whether there will exist some n0 starting from where the gap is going to close, right? So this is all this is to make the important point that the spectra are very, very complicated, and not much can be said in general about them, right? But it turns out if we ask a more modest question about the energy density, things get much simpler. So imagine the spectrum of a many-body Hamiltonian, right? In principle, if you have, for example, n particles in your system, and each particle has local dimension d, then we know that the Hilbert space dimension is going to be d to the power of n, right? So we are going to have d to the power of n levels in general. And on the other hand, if the Hamiltonian is local, namely the Hamiltonian is just a sum, even if of interacting terms like ij's, but only of local terms, right? Some ai times, I don't know, aj, right? Living in different subsets of your, you can imagine a lattice, right? Always a many-body system can be imagined like a, yes, it can be imagined as a lattice, right? For example. So given this structure, we immediately see that the energy, like the minimum energy, so this is going to be the E minimum. Oh, I'm sorry. E minimum, and this is going to be E maximum, right? Sorry. Well, anyway, so you see the point, right? So this is the minimum, this is the maximum, and we know that this E max is going to be proportional to is going to scale with n, right? So what we see is that in a gap, in an energy range of width n, we have to fit d to the power of n amount of levels. This means that the packing of energy levels is exponential. It means that in general, the distance between the levels is going to be shrinking exponentially with n. So this is the general rule of thumb. Of course, there can be some degeneracies, but we will see that this is not going to be the case in general. So given this premise, we can think about the density of the spectrum, right? And the density is going to be given by the following thing. So imagine you have like an energy level around energy E, you're interested in energy E, which is around some level here. And then we take some gap, delta E, and consider the number of energy levels within this energy range delta E. So this is going to be the delta N. Then in principle, we can write this as this quantity where this omega E is kind of the energy, is the density of energy levels and is a function of E. Of course, when we move up or down the scale, the density of this energy levels is going to change, right? Now, once given this density, now we can ask about the plane probability distribution of energy, right? We don't ask about each energy level, but we say, okay, so imagine I measure the energy of this many-body system, right? What is the probability that I will find value of E, like within a given range dE, right? Or delta E or something like that. Now, then this is going to be given by the second formula here. If the many-body system is in a thermal state, which is going to be, of course, the other assumption that we make, we say that the system is in a thermal state, right? So this is an important premise. So once given a thermal state, and we know that the thermal state is characterized by the following thing, right? So it is given by this formula, by this object, which should be interpreted as the probability of finding the eigenvalue I is equal to e to the minus beta ei over z, where z is the normalization constant, which is also known as a partition sum. Everybody, I think, knows that. So what is the point here is that, yes, so now if you just ask about the plane measure of probability, namely, if I'm given an energy range E around some value E, what is the probability of finding a level here, then this can be written as the energy density times this Boltzmann factor times DE, right? So this is the way we define this PE, right? So the rest of the paper, the rest of the seminar, the rest of this talk is going to be devoted to this quantity PE, right? Okay, so let's see what is known about this quantity PE, what has been known so far about this this quantity, and this thing that has been known about it is called many-body Berry-Esseen theorem, and it holds under these two assumptions. So this is assumption number one, right? So imagine that you have a many-body system, which I'm for simplicity representing as a lattice, but it doesn't have to be a lattice. It doesn't even have to be regular for this theorem to hold. And then you have, let's say, two regions. So this is region X, and this is region Y. And you have two operators, X and Y, on these regions, X and Y. And the distance between these regions is L, suppose. Right? Now, if I calculate this quantity, like X times Y, and take the average over the global thermal state of the lattice, and destruct the local average, the product of local averages, and normalize it with the norms of this operators X and Y defined on regions X and Y, then what I should have is that this object decays exponentially with the distance. Okay, so
since you stopped, so you are supposed to make stops every 10 minutes, and this is already almost 10 minutes. So I wanted to ask a question.
Oh, yes, sure. I mean, you can interrupt me at any time.
Okay, but yeah, let me just ask you this. So you first say that the X and Y are some regions, and then you take their product. What does that mean? Any characteristic of the system over the region X, or what is X and Y that you are taking products of?
Oh yes, that is a good question. So imagine these two regions that, let's, for avoiding confusion, call them region A and region B. And these are two disjoint regions of the lattice, right? Now, let's take some operator X that lives in the local Hilbert space defined by this region A. Let's call it HA, and Y is in HB. These are two Hermitian operators, in principle, arbitrary, right? And now I construct this quantity, this correlator, right, for arbitrary X and Y. And we require that this object decays exponentially like this, right, with the distance between the regions A and B for arbitrary X and Y localized to regions A and B. So this is the condition. Basically, this shows that this decay of correlations is a generic property of the state of your system because it holds for arbitrary operators. It's not a peculiarity related to the way you choose the two operators in regions A and B. Does that make sense?
Yes.
Okay, very good. So so we have this requirement of exponentially decaying correlations. And the second condition is this, which is the standard deviation of the Hamiltonian. So basically, we define sigma h square as the difference between this thing. So it is the standard variation definition here, and then we require that it should be proportional to n, where s here is some proportionality constant, right? So basically, these two requirements, they fix a many-body system which is not at a phase transition, right? Correlations decay exponentially, and the variation of the Hamiltonian is oh, I'm sorry. So this sigma is already a square. I'm sorry. Yes. So the variation of the Hamiltonian is proportional to n, so that the standard deviation, which is the square root of this guy, is proportional to square root of n. So this is the standard, like central limit theorem limit kind of many-body systems. And if this holds, then the following inequality holds too. So I will tell you the meaning of the quantities here. So Fe here is the cumulative distribution function for the actual probability distribution. So if we go back, right, I mean, I will not go back because it apparently doesn't work so well. So as we define, this Pe is equal to density of states times the Boltzmann factor, right? And this is something that that doesn't even have to be nice. It's not analytic because it depends on discrete levels and stuff like that. But of course we consider an analytic limit of this thing, and we define this Fe as E minimum, some value of E, d E prime P E prime. So this is the standard definition of the cumulative distribution function, and GE is the cumulative distribution function for the Gaussian distribution. So GE is the cumulative of this GE, which is simply e to the minus h minus average h square over Sn, which is like the sigma h. Okay, let me actually fix the sigma h. Sigma h over normalization constant. Right. So basically, what this theorem is saying is that in the limit, in the thermodynamic limit, namely when n goes to infinity, these two cumulative distribution functions, they converge. So in other words, the energy distribution of a many-body system with some completely unknown to us spectrum is just given by a simple Gaussian distribution. All right, so this is a very powerful statement about many-body systems, which kind of gives us a way, and it is very similar to the well-known Berry-Esseen theorem from usual mathematical standard Berry-Esseen theorem, which says that if you have just a sum of random variables, let's say you just have like x1 plus xn, and they just have a standard variation sigma I and stuff like that. But once you normalize those guys, right, like xn square, then this random variable is given by a Gaussian distribution too. So this is the standard mathematical Berry-Esseen theorem, which is generalization of the central limit theorem. And here we have the same statement for many-body systems, where we don't have nice random variables just summed together like classical quantities. We have terms in the Hamiltonian which do not commute among each other, right? So this is sort of the generalization of this concept. That's why it is called the many-body Berry-Esseen theorem. Okay, so this brings us precisely to the motivation of the work that we have carried out in the paper that I mentioned, where our aim was to somehow extend this Berry-Esseen theorem to critical systems, namely to systems for which this condition, this condition, right, does not hold. So the correlators, they do not decay exponentially. For example, they may decay polynomially. So you have x xy minus xy is proportional to some psi l to the power of a, where a is something larger than 0, right? So this is a power law decay, which is a standard marker of a phase transition in a many-body system. So this clearly violates the this condition, all right? So the already proven many-body Berry-Esseen theorem does not hold in this limit. So our approach to proving this theorem now is going to be as follows, right?
Gaussian, I'm sorry, Gaussian. Before you prove the theorem, may I ask a quick question?
Sure.
So you said that there's a classical Berry-Esseen theorem where you have like n random variables x1 to xn, right?
Yes.
And you said it's a generalization of the central limit theorem.
Yes.
So, am I understanding correctly when I say that the generalization is in the fact that they're no longer independent and identically distributed? Like, is that where it's generalized? Or are they still independent, but the probability distributions can be different?
Yes. So in the classical Berry-Esseen, x1 and xi are independent, but they are not identical. So their variations can be sigma I, and sigma I does not have to be equal to sigma j. So this is the generalization.
How about the averages? Their averages are the same.
Well, in principle, you can just by manipulating constants, you can just say that the average of all of them is 0, right? So this is something that doesn't make you lose generality.
Oh yeah, okay, yeah. You can just redefine your random variable to be average 0, I guess. Okay, fine. Yeah. Exactly. Thank you, Gaussian.
I wanted to say that the sigmas are larger than 0, but well. Okay, so yes, so let's proceed with the proof. It's going to be a bit technical. I'm going to jump over certain points, and basically I'm going to present the kind of the main results that are going to contribute to this proof. So imagine you have a many. So okay, to start with, the result that we have here applies only to translation invariant systems. The previous result was not limited to translation invariant lattices, but here there are some limitations, so I'm going to list those limitations. So translation invariance is one requirement. The second requirement is that we just have a lattice system with local Hilbert space dimensions. So basically we have like a regular lattice over here, and each node, let's say it is node A, then the dimensionality of the Hilbert space around this A, right? So let's make it curvy so that we don't confuse it with the Hamiltonian, is equal to some d which is not infinity. So something like this. So this is the kind of main kind of setting here. Now for these types of systems, there exist several classical theorems, especially ones by Araki. There are several papers. So I'm just going to give his name, and I'm sure that once Googled, you will find those statements. So the main statements here are as follows. If we look at the energy, right, energy density, so there exists the following limit n goes to infinity. Omega hn over n, and we will call this u omega. So the meaning of this expression is as follows. Imagine you have a lattice of finite size, of size n, and on this lattice you define your state omega n. For simplicity, imagine that we make the ends meet, right? So this is like a not just a line, but rather let me show it. It's rather a ring. So basically, we just have a set of rings. So basically, you just have these circles with particles, and your state on this n-node circle is translational invariance. So basically, you go from you just rotate by one node here, right? So you just go like this, and your state doesn't change. So this is the definition of translation invariance, and we consider this omega n's up to n goes to infinity, right? So this is a set of states like this, and we will call this a translation invariant state on an infinite lattice. That this limit n goes to infinity, omega n, right?
So your lattice is supposed to be 1D, or it can be.
Well, in principle, it can be of arbitrary dimension. This ring shape was mentioned for simplicity. In principle, you can imagine something open-ended and just keep increasing its size, and again defining these omega n's, which are translationally invariant except for the edges, right? And then you just connect, for example, omega n to omega n plus 1 by requiring all the overlapping nodes to have the same partial state. Okay, this slide is a bit ugly already. So let's imagine a very simple situation. So I have like 4 nodes here. So this is my n equal to 4. And then I have, for example, n equal to 6, right? So I go to the next level, n equals to 6. I have overlapping sides here, right? So here I have my omega 4, and here I have my omega 6. And what I require is that the reduction of omega 6, right, so trace over, let's call these guys tails, right? So tail. So trace over tail of omega 6 is equal to omega 4, right? So this is kind of the relation between larger omega and smaller omega. And then we increase n infinitely. And what we require is that this omega 4 or omega 6 are translation invariant except for the, of course, except for the edges, right? So if we switch this block one node to this part, then we're going to get the same state, again assuming that there are some edges left, right? So this is a bit tricky, but I think in principle it's quite intuitively clear what it means to have a translationally invariant lattice, because, like, again, you just consider the bulk, you forget about the edges, and then things look like very translation symmetric. So this is the assumption. I hope it is clear now. Okay, so actually try to go back. I lost the trail. Oh yes. So given that we have this infinite infinite series of states and an infinite series of Hamiltonians on these n-dimensional lattices, which are also going to be translation invariant again, right? We can define this ratio. We just take the average energy divided by n, and then we obtain the energy density. And one theorem by Araki says that this u omega exists, right? So this is a very important thing to note. So this is one. Two, what another theorem of Araki says is that the following limit also exists. So if we take minus trace omega n ln omega n divided by n, Okay, so I hope it is clear, but let me clarify this point, that the entropy is defined here as the von Neumann entropy, which is like this. Imagine you have an arbitrary state rho of an arbitrary quantum system, right? Then you say that the entropy of this state is equal to this. It is the trace of this object. Now, if we take the von Neumann entropy of the lattice here, right? It is this object with the minus. Okay, let me actually bring the minus here. And divide it by n, we get the entropy density. And this guy also exists, right? Good. So the third theorem by Araki says the following thing. It's called the variational principle. So we take u omega and we construct this object. And we consider the infimum of this guy over all translation invariant states, right? And then we will obtain the free energy density here. So this is a very non-trivial statement, especially when we consider that this objects do not have to be analytical functions because of the thermodynamic limit taken. But this holds true whether your system is critical or non-critical. Like it works all the time. So to get a better intuition about this thing, let's just remember the following thing from thermodynamics, right? So in thermodynamics there is the Helmholtz free energy, right? Which we usually write like this. We say this F, the free energy, is equal to energy minus temperature times the entropy, right? And one principle that we have is the maximum entropy principle, right? So when you consider states of average energy E, right? So imagine you have an arbitrary system which is in a state rho, and then you say that you pose the following condition, right? E. So you want your average energy to be equal to some number E, right? So you want your trace rho H to be equal to E, right? Now, the state that maximizes the entropy for this value of E is going to be the thermal state. So, arg max of this guy of minus trace rho ln rho under this condition is going to be equal to the thermal state, which is the e to the minus beta h over z, where this beta, which is going to be the temperature or the inverse temperature. So I'm going to use these two guys interchangeably. So whenever I say beta, I mean 1 over T, and when I say T, I mean 1 over beta, right? So, and this beta is to be determined back from this condition, right? So basically the non-explicit equation for beta is given by this thing, right? So it's H minus beta H over trace beta H, right? So this is the formula for beta. So basically we have that beta is a function of E, and it is very easy to show that this is a monotonic function. So the higher the temperature, the higher the energy. So this guy is a monotonic function of beta, and there is only one place where it meets this line E, right? So this is the thermodynamic background of this thing, and of course this maximal entropy principle can be translated. It's maybe not so trivial, but I'm not going to dwell on it even longer because I've already talked about this so much. What we have here is that if we construct this quantity, right? If we just rewrite this guy, right? E minus Ts, right? So we can say that this guy is equal to, this is a functional of the state now, right? It is equal to trace H rho plus T trace rho ln rho. Right. So now if we want to minimize over rho this quantity, then we are going to get this object, this f beta, which is the T ln z, right? This is the very well-known formula from standard classical mechanics. This is the formula that everybody uses in the university course of statistical mechanics to calculate pretty much everything you require, right? So this is the formula. And this is a consequence of this variational principle. So basically, this guy is the thermal. This principle is kind of the guarantee of the stability of the thermal state. So basically, you take this energetic quantity, and then you know that its minimum is met, is achieved by the thermal state. So this is the kind of thing. And then if we go back to our many-body setting, so this is going to be the variational principle, right? Where this Ft now, this Ft, is of course going to be this object, right? Limit n goes to infinity, again, Fn as a function of t over n. So this is the free energy density, this is the energy density, and this is the entropy density. So this we're going to use extensively. But since I'm running out of time, I will, say two more important things, and then we'll jump to the results. Okay. So if you do have any questions, I have a sensation that I've introduced a bunch of quantities and notions, so it might not necessarily be very clear which goes where. So if you have any questions, please feel free to ask them now. Okay, so if you don't have questions, so let me state the following lemma, which is very important. It is proven in this paper. Let me actually write it down for you. It's Müller et al. It's Communications of Mathematical Physics 34044.
Karen, sorry to interrupt.
Sure.
You know that we started late and you still have 25 minutes.
Oh yes. Actually, I didn't take that into account. Well, that's excellent. I will just go on for as long as I can.
Okay.
All right. Very good. So let me fix this point. Okay, so good. So the following result has been proven in this reference, among other things. All right, so let's denote by Qn U the number of eigenvalues of Hn which are smaller or equal than U times n. So basically what we're saying is that since these u's are going to serve as energy densities, so I'm saying that I fix an energy level which equals to this guy of this many-body system, and this QNU is the amount of energy levels that the Hamiltonian Hn has below this energy, right? Now, what has been proven in this work is that the following. Basically, it's this limit of Ln QNU over n is equal to S U. Now, let's come back to SU, right? So, okay, all quantities here are clear, right? So we take this this quantity, which is basically the amount of energy levels up to a certain energy. We take its logarithm. We look at its density, and then the claim is that this object is equal to the entropy density here. Now, as we have established before, let me try to get this. Yes. When we minimize this object, right, we get to this thermal state here. And yes, and for this thermal state, we can now calculate the entropy, right? So basically, let me actually go even further than this, and sorry. Yes, let's come back here. Okay, so what we're saying is this, right? So for each value of energy, right, the maximization of the entropy happens for a thermal state, right? So for each value of energy, we have a beta, and for each beta, we have an entropy defined by the thermal state. So basically, we just substitute this thermal state to this rho, and then we find the entropy here. So basically, what we have thus is that entropy density is a function of energy, and also as I showed below, beta is also a function of u, for example. So all these things are mutually expressible, and it can be shown that these functions are unique. So basically, you can define these things uniquely. Okay, very good. So having established this,
so can I interrupt you with a question?
Oh, hi. Yes, of course.
So this is just a microcanonical theorem, right?
Yes.
You are supposed to know it. It's just telling that canonic entropy is the same as microcanonical one, because it
Exactly.
defines the density of states. So
Yes.
then what is new in this theorem? Why it has to be proven in such a
Okay. So
difficult way?
let me. So this was actually my next slide. So let me just go on, and hopefully it will become clear. But yes, the bottom line is that, of course, this object, the logarithm of this guy is the microcanonical entropy, and yes, and it is shown that its density is equal to the density of the canonical entropy. What is special about this is the following, right? When we have a phase transition, actually, I have to go back. When we have a phase transition, it is very stubborn. I'm very sorry for this. Yes. So I was talking about this variational principle, right? And Now let us assume, well, no, not assume. So let us go to the regime where the Gibbs state is not unique. So let's go to a phase transition point, right? So this equality that this this statement that the infimum of this object is equal to this thermal free energy density holds only when there is only one state that delivers this infimum, right? So when this KMS state, as you could also call it, because this basically defines the KMS state. So the omega that delivers the infimum is called the KMS under a temperature T, right? So when it is unique, then we know that it is the thermal state. But when we are at a phase transition, for example, it may not necessarily be unique, right? Which is basically the coexistence of several phases, right? In this case, in that case, this result becomes very important to have this. It becomes very important to have this relation proven rigorously, because now the basic intuition that the microcanonical and canonical ensembles coincide may no longer be the case, because you have strong correlations in your system, and it's not guaranteed that all these things will coincide. So basically, what this thing proves is that this relation is correct irrespective of whether you are at a phase transition or not. So that is the kind of the fundamental value of this thing, and this is what is going to allow us to expand this Berry-Esseen statement to the critical regime. Okay, so now I'm going to make several analyticity assumptions, which are not going to be very palatable for mathematicians, but well, that's life. So as we define this Qn, right? So okay, so now having this object Qn defined, right, as this number of Ek such as they are smaller than Un. Through this object, we can define the energy density as we defined it before, right? So let's define it like this. So omega Ne is equal to this derivative of Qn u over n du. Here again, E is equal to n u. I'm again changing things, using things interchangeably. So as always, beta is equal to 1 over t, in case this comes up. Anyway, so we have this quantity here, right? And now from this statement here, that was proven in that paper by Müller et al., which is this, it's Qn over n is equal to Su, right? So we can collect those two things into the following statement, that omega Ne is equal to En Sn u plus O big 1. Okay, so this is going to be the most fundamental kind of relation that we're going to use in what follows. And this is again true whether your system happens to be critical or non-critical. So this is true all the time, as long as the Hamiltonian is translation invariant, it is local, and that's it. Good. So all in all, with these things already established, we have the following relation in place, right? So the probability density for the energy is equal to 1 over Zn, right, e to the minus beta e, right, times this Qn e, right? So in other words, and well, I mean, just so it is obvious again, as we know, the thermal free energy is equal to this thing, right? It is the TLNZ with minus.
Yeah, can I ask a question?
Sure, sure.
Now you say probability density, but the probability density should not contain Qn, which is the number of eigenvalues just smaller than E.
Oh no, you're
It should
completely
be
correct.
eigenvalues. It should be the number of eigenvalues between E and then E plus delta E, right?
Exactly. I'm sorry. It was a typo, and thanks for pointing it out. So basically, this probability density is indeed, as I said also at the beginning. So it is this, right? So Qn, like let's call it a delta, right? And let's drop the n because it just complicates things. So Qn delta E is indeed going to be this, right? So it's the probability of finding an E in the interval, in the small interval delta E, times the amount of energy levels in this interval delta E, which is going to be given by omega E delta E. So this is the intuition behind this formula right here. So yes.
Gaussian, also, if I may ask you another question, can you go back to the previous slide, please?
Sure. Let me see if I manage to.
Sure.
Okay.
Okay, great. I wanted to ask you about the last formula that you got. So is this formula correct for any n, or is it only correct for the limit, for the thermodynamical limit?
Well, as you see here, there is this object, which is O big one. So of course, this statement is meaningful only in the limit of large n. So we should have n large so that this object is not relevant anymore, because when n is like, I don't know, 10, then these two guys are of the same order, and since we don't know what this O big one is, then this formula becomes useless. So yes, this is a formula meaningful only for large n.
Mm-hmm. Okay, in that case, how does the result that Muller got is relevant for this one? Because we're not using that entropy, right? We're using the entropy as a function of n. We're not using the limiting entropy.
Oh yes. I will get there. I will get there.
Okay. Okay. Thank you, Gaussian. I'll wait for that.
Oh no, actually, I'm sorry. Yes, you're completely right, and this is a point that I jumped over. So it is correct. So what is the source of this O1, right? Let me be clear about this. So this is an important point. Let's be careful about this thing. Indeed. So. Yes, right. So the result by Muller is the following, right? It says that, I'm sorry, ln Qn, right, is equal to Sn, right? And since this is true only in the limit, we can say that this guy is some O small n, right? So this O small n is defined as I mean, O small n means that if you divide this guy by n and take n to infinity, it goes to 0, right? So it is something that scales slower than n, right?
Right.
Okay. Now, and then there is another, let's say, rigorous result that is super intuitive. So I'm not going to even mention whose result is that. Is that if S is basically the limit of n goes to infinity of large S over n, right? Which is the small Sn here, right? So basically, since this is the case, right? Then what we have is that S equals to Sn, right? Plus O small 1. Now, it can be shown quite rigorously for arbitrary dimensional systems that this small object here, it is an older result by Berry-Esseen. This object here is actually equal to O. Let me see here. Yes, it doesn't work. O1 over n. Right. So you can see what I wrote. No, I mean it doesn't look very pretty, but hopefully it's clear.
Yeah, it is clear.
Okay, very good. So basically, what it says is that boundary terms don't matter. So so basically, the infinite n limit entropy density is the entropy density for finite n plus something that just accounts for the boundary, right? And so if we combine this guy and this guy, we just get this formula here. So this is the logic behind this formula.
I see. Thank you, Gordon. Thank you.
Good. Okay, so where were we? Right. Yeah. Okay. So yes, if we remember about this formula and then again introduce the density here. So basically, write n fn beta, where fn beta is just fn over n, right? We can rewrite the above formula as the following. So basically, what we have shown here is QNE is equal to E beta n Fn minus beta n U minus T Sn U plus O large 1. So okay, so plus something that we are going to neglect anyway. Okay, so now it takes some time to properly think about what this formula means, right? Okay, so let's remember. Let's go back to the variational principle, right? Now, what the variational principle tells us is that this guy here, this object U minus T S N U is going to be it is going to be minimal for the thermal U. So whenever we go back to when U is equal to U as a function of beta, right? Where U as a function of beta is again defined as, so UN beta is equal to 1 over n trace h beta h trace e to the minus beta h, right? So basically, this is just the average energy of the thermal state. And yes, so if we just take arg min of this guy, it is going to be the UN beta, and the minimum value of this guy is going to be the Fn. So minimum of this object is going to be Sn U, right? It's going to be Fn. So what these things mean is that this QNE is a function like this, right? Where this is the Q and this is the E, such that the maximum is met at E beta, basically. right? And when you go further from the state, this thing decays. And actually, this point can be made again very rigorous by, again, I have to invoke a ready result because all these things are I don't know, they're proven somewhere, and it's not easy to prove those results in general. So if we take this object, right? So u minus t s u, right? So let's take a look at this object. Now t now here is just a parameter, right? And s is just a function of u, in a sense that, for example, if we take some energy u, right, it is going to be the thermal average energy density for some temperature. Let's call this temperature T prime, right? So it's going to be the energy for T prime. And then for the same T prime, we're going to calculate the entropy, right? So in this sense, we say that the entropy, that this SU is exactly in this sense, right? So, and this function can be shown to be strictly concave, right? So if we now paint this guy, so let's call this f as a function of u. So we have the f and we have the u. This guy is strictly, oh, sorry, I'm sorry. This is actually, this function has to be convex. I confused myself here. Actually makes much more sense. So this guy has to be strictly convex, and again, its minimum is met at the u beta, right? And of course, it is this result that we invoke here, that we just substitute in this formula, right? If we look at this formula and then we look at this convexity result, right, we obtain this object. Okay, this statement, I'm sorry. So what we can say in general already here is that the energy density, the energy distribution, I'm sorry, this energy distribution here is a unimodal distribution centered at the average energy. So if we have a thermal translation invariant system, then we know that its energy density is going to be of this form. And then again, coming back to this formula here, I'll actually clear it up so that it's a bit more evident because I keep coming back to it.
Karen,
Yes?
yeah, I just wanted to let you know that there's basically it's already 1 hour, but you can go on.
Okay, I will wrap this up like within several minutes.
Yeah, okay. So just to let you know, not that I mind if you go, but
very good. Well, so let's look at this formula again, right? Let me get rid of this line here to draw it right now again. So when we look at this difference, right, we see that it is exactly the difference between this guy here, this line, right, this value f beta, and one of these guys here. So if for example u is this object, then this difference in the exponent, right, is equal to this, let's call this delta f, right? We have that it is e to the minus n beta delta f, right? So what does it mean is that if we go away from the average energy here, right, we go to some e, so that e minus e beta is proportional to n delta. This delta can be an arbitrary small number. It just, this difference has to scale with n, for example, right? then in this case, we can say that the probability here, this Q of E here is this object, basically. So it is exponentially decaying as we go further to the tails of this distribution. So this is an important observation, that even if the tails are not Gaussian, and I will now show that they are not always have to be Gaussian, right? Even if they are not Gaussian, we know that they definitely, once we are you know, far enough from the average energy, these guys are going to decay exponentially, right? Okay, so this is one main observation. So somehow, although all the rigorous results that went into this observation have been known before, this thing was not known before, right? That this unimodality can be obtained in such a way. Now, what one can do is basically use again this formula here, right? And then Taylor expand this quantity because we know that this U minus TS, right? Its minimum is at Fn, and then if we depart a little bit, if we go to U plus some epsilon, right? Then we can Taylor expand this function around the Fn, and then find better a better approximation for the actual Q and E when E is close to the average energy, right? So this is going to be a key point here. And I'm not going to go into details because I'm already over time, but basically what you can show non-perturbatively, which would require, of course, assuming analyticity. So basically you assume that all the derivatives exist. So you can just estimate all the terms and then non-perturbatively show that when your system is critical with alpha equals to 0, and I will clarify what this means. So now we have critical systems. So now there is alpha equal to 0 and there is alpha larger than 0. Now these are mildly critical systems. These are strongly critical systems. And again, I will make this precise a bit later. So for mildly critical systems, the ones the divergence of which scales logarithmically, for those things we can show that again that the probability distribution here, QNE goes to GE as n goes to infinity, right? Where GE is the Gaussian distribution. So basically it is e to the minus E minus average energy square divided by 2 sigma h, where sigma h is the standard deviation of the Hamiltonian. And note that this guy is now going to be divergent. I mean, it's now this guy is not good. Now the sigma h is not going to be proportional to n. It is going to scale larger. And when alpha is larger than 0, we do not have this thing. We have this convergence only for very small values around the peak. So only in a very narrow part of the peak we have that the distribution is Gaussian. So this is pretty useless. And essentially what we're left with is this unimodality with exponential decay, as I said. So basically when we go to strongly diverging systems, then all we have is unimodality. And if it's mildly diverging, then we have again Gaussianity in a strong sense, which is point by point. So for each Q and E, for each value of E, when n goes to infinity, you just get a Gaussian distribution. And so let me now briefly mention what these alphas are. So when so imagine you have a system, right, in a thermal state, and it has energy E. Now, if you take the derivative of this E over T, basically determining the sensitivity of energy with respect to temperature, right, you get the heat capacity. So basically, this is the amount of energy that you have to spend to change the temperature of the system by 1 degree, right? And this is a function of temperature. Now, at the point of second order of a finite temperature, finite T phase transition, right? So let's take a point of finite temperature phase transition, right? Then, and which happens at temperature Tc, right? Then we know that the Ct is going to diverge around Tc. Now there are two types of divergence. One type of divergence is like this. It is logarithm of T minus Tc, right? So this is one type of, and I'm going to need this to be the density. Okay. So this is the mild divergence. This is the alpha equals to 0. And this is strong divergence, which is 1 over T minus Tc. Maybe we can add a Tc for dimensionality reasons, to the power alpha, where alpha is larger than 0. Right, so when we put alpha to 0, we could have like, this could just be proportional to 1, but this means non-criticality, because this would mean that the heat capacity does not diverge. But when alpha goes to 0, the other possibility is a logarithm, and then you can show that basically logarithm is all you can have, right? This can be shown quite generally for generic many-body systems, right? So the alpha equals to 0 is like in the previous slide was meant exactly in this sense, that Ct is proportional to T minus Tc logarithmically. And then when we go to finite size systems, what this means is that this Cn is proportional to logarithm n, right? It can be shown that this leads to this thing. And since this is the heat capacity density, the specific heat, then the full heat capacity scales as n ln n, right? So this is the scaling here. And the final piece of information that is necessary is that let me see, is that the heat capacity is proportional to sigma h. Sigma h. So this is a very simple calculation. So basically the variance of h of the Hamiltonian gives the heat capacity. And then what we have shown there is that the Gaussian is that the energy distribution of a critical system whose variance scales as n ln n goes to a Gaussian distribution, just like we had it for the Berry-Esseen theorem over here, where the sigma h had to be proportional to n, right? So basically we extended this statement to n ln n, and when we have n1 plus some positive alpha, then we basically say that it doesn't have to be Gaussian, but it's still unimodal with exponentially decaying tails. So basically these are all the results that I wanted to present today, and thank you for your attention.
Thank you. We can ask a few questions. Anyone? I have a quick question. So the formulation of the theorem for the critical systems does not have any difference from the one that you can formulate for standard case?
Oh no, it does actually. This is also an important question. So basically, the statement here is slightly different, right? So the standard case was this, right? Standard was saying if I take the cumulative distribution, the actual distribution minus cumulative distribution of a Gaussian distribution, right? Then I take the absolute value and I take the supremum of this object with respect to E, then it is going to be smaller or equal than logarithm n over square root of n with some spatial dimensionality here, right? So it's going to 0 as n goes to infinity. So this is the statement here. The statement that I proved is this, right? So it's that QE, let me show it here, GN, right? QNE goes to G and E, where this Q and G are the probability distribution, are the derivatives of these guys, point by point. So for each fixed energy here, as n goes to infinity, I have this convergence. So these two things are going to be more or less the same in most cases, but in principle, this point by point divergence is slightly weaker than this thing because I can, converge to something point by point, but for various values of E, this difference can still increase, and maybe when I calculate the cumulative difference, then it may not necessarily go to 0. So this is a subtle difference here, which is not very crucial because of the fact of exponential decay at the tails. So I haven't proven that rigorously yet, but I think because of this exponential decay at the tails, this thing is going to be equivalent to this, at least with some very minor assumptions, extra assumptions. So yes, this is an important difference between the two formulations.
Sorry, maybe an irrelevant question. That E, the range of the parameter E, is it the real line, or is it somehow is it normalized to be the real line for all n, or is it does it change with n?
Well, yes, it can change with n, of course. Let me clarify. Basically, what we have here is again a system, right? We have a many-body system with some spectrum, blah blah blah, right? So the energy of the ground state we can always put to 0 because, well, it doesn't matter how you normalize this thing. And then we have this Emax, which is going to be proportional to n. So for large n, and well, so this is point 1, right? Now, this average energy, so energy density equals to 0 is achieved for temperature equals to 0 if there is a gap, right? So roughly speaking. And this U equals to E max n is going to be achieved when T equals precisely to infinity, right? And of course, all the considerations that I was making here was happening for T, which is neither 0 nor infinity. So it means that I'm somewhere here, and it is some U times n, and U minus E max over n is, well, actually converse, right? E max over n minus U is lower bounded by some positive number. Anyways.
So maybe I'm asking something much simpler. So basically, when you say that a certain sequence of functions converger has a limit, or when you write something an asymptotic formula, so you assume that there should be a common domain for all these functions. So I assume that the parameter E, which is the parameter for all those functions in the sequence, should reside in a common domain. Because if the domain is 0 to n, say, it evolves with n, and it it's not clear to me how you define pointwise convergence if the domains are different.
Okay, yeah, my answer was too long and not to the point then. So the bottom line here is the following. Basically, the reason why I always was talking about the densities is because the range of densities, basically this U mean and U, sorry, U max. This thing gets stabilized very early. So for large enough n's, starting from some value, let's say 10, 12, right? This range remains pretty much fixed. And we work in this range. That's why I always talk about the densities.
All right, so on the previous slide, you formulated it in terms of E, right? So you
Yes,
say
yes.
here the convergence is pointwise for every E. So where does the E belong?
Okay, so this is again a very good question. So let me just rewrite it in a more precise form that it should actually have been, because this was like me trying to be more intuitive, but actually no. So we have this thing un for arbitrary u in that range. You know. So this is the formulation.
But what do we mean by Qn converging to something that depends on n?
Oh, yes. Okay, so what we have here is Qn with this argument minus Gn goes to 0 as n goes to infinity. Basically, this is
okay. So should I understand it as follows, that
and this Gn when normalized to densities, it goes to some fixed Gu. Like, I mean, it's not something like jumps about, right? It is a definite thing which can be formulated as, which is basically e to the minus u square over the variance of u. So basically this is with normalization. So basically this G goes to this thing.
Fine. So what I'm trying to say is that all those asymptotic formulae with little and big O notations and all these limits, they're understood as with respect to a parameter u which is on a compact interval, right?
Yes.
Because every time I was looking through it, and I had the worries that whether or not this asymptotic formulae hold uniformly. So if u is in a compact interval, then the odds are that it is indeed uniform, and that sort of clears things up a little bit. So
okay.
One more comment I wanted to make is regarding the classical Berry-Esseen theorem in statistics. So maybe the way I understand it is the classical Berry-Esseen theorem, the variations of individual random variables isn't very relevant there. You can always sort of normalize them to be 1, and you can normalize the the expectation value to be 0. But the point is that it's probably not a generalization of the central limit theorem, but rather an improvement under extra condition that the third moments exist.
Yes.
So the central limit theorem tells you that the average of random variables, identical and independent, tends to a Gaussian. But then it doesn't say anything about the rate of this convergence. Whereas the Berry-Esseen theorem tells you that, well, if you in addition assume that the third moment is finite, then there is a quantitative measure of how fast actually, at least, this convergence takes place. And yeah, it's otherwise it's the same formulation as the normal central limit theorem. Yeah.
Well, I of course agree with you with what you are saying, but it has to be noted that of course Berry-Esseen assumes the existence of the third moments, but then it gives you the extra freedom of taking the sigmas to be different, which cannot always be trivially reduced to IID. So basically, these guys, I mean, you get more generality on IID-ness, which you don't have to be IID. But then, of course, you need the third moments indeed. Yes, I think that's the note, the difference.
Well, I'm not aware of the version of Berry-Esseen where the sigmas are written as different, and to my understanding, you can always normalize them. So I don't see why different sigma i's would cause a problem, but that's probably a matter of a separate discussion.
Okay, interesting. Yeah. All right.
Yusuf, can I ask a question?
Yes.
Okay, so I'm a little bit lost with those various formulas. Let me try to understand by words. So we say macrocanonical theorem, and we understand that basically the statement that macrocanonical entropy is equal to the canonical one. Now, if I try to summarize your result by a few words, are you telling that if alpha is 0, then the generalization of this macrocanonical theorem is smooth, like you just proceed with it? And if alpha is larger than 0, then you have troubles there? Can you summarize it like this?
That's a good question. Let me think about it. Well, I think these two are a bit independent statements because let me show this thing again.
Just for me to follow the discussion, alpha is the critical exponent, right?
Yes.
And when it's 0, it's actually diverging much slower than when it's bigger than 0.
Yes. Yes. When it's bigger than 0, then the divergence is polynomial, and when it's 0, it's logarithmic.
But in the non-critical systems, it's exponential divergence, even faster, right?
In non-critical systems, yes. No, wait. So when we say divergence, we mean the divergence of the heat capacity, not of the correlation length, not of the correlations. So
okay, okay. So now you're not talking about the divergence of correlations. So this exponent is not about correlation.
No.
Okay, I'm lost. So maybe you can.
Yeah. Okay. So let me address Armin's questions, and then I will come back to this exponent thing, if that's okay. Well, so what I was trying to say. Yeah. Anyway, so this statement that yes. So this formula here that we have, right? This is basically the statement of the canonical equivalence, right? This is the microcanonical entropy, well, the logarithm of this guy, and this is the canonical entropy, and their equality is true whether alpha is 0 or it's larger than 0. Basically, this Gaussianity and non-Gaussianity is more about the way the variation principle works. I mean, basically, when you have Gaussian thing, when you have Gaussian Gaussianity of the probability distribution is equivalent to stating that U minus TSU diverges from F as U goes away from the average as a U square, basically, right? And when alpha is not 0, then this is not U square. This is some U alpha. Well, I mean, let's not confuse alphas. Some U, I don't know, A.
Okay. Yeah, it's clear. So it's about the asymptotic convergence of the canonical to microcanonical.
Yes, yes. How they converge? Yes, it's more
I
about.
have another question. So, if I'm not mistaken, this alpha equal to 0 is really very much unstable thing, because there is a criterion, I don't remember whose name is that, telling that if you have critical system with alpha equal to 0, then it is unstable with respect to arbitrarily small disorder. For instance, this alpha equal to 0 is a critical behavior of two-dimensional Ising model, right?
Yes.
And then if you bring the small disorder, then it changes to a double logarithm. So what I want to say is that this alpha equal to 0 is generically unstable somehow with respect to various perturbations. And I mean small perturbations even.
Okay, well, I mean, this is something that I did not know, so I don't know how to comment on that, but I will definitely kind of look it up to see how it works. Because so basically the claim is that if you add some sort of perturbation to the Ising model, then all of a sudden alpha becomes larger than 0. Is that the claim?
No, it can become anything. It's like you have to do and to see. So various examples. There is a theory on that. I don't remember details, but what I know is that somehow alpha equal to 0 is unstable, which means that you are not going to see it regularly, only maybe in very specific cases.
Okay, so well, if that's a very general statement, then maybe this result of ours can kind of shows that in the generic criticality, basically you don't have Gaussian, right?
Yes,
if opposes
so that puts some weight. That puts some weight on your results. If you just figure that out, it may increase the relevance of your result.
Okay, thank you for that comment. I mean, I will try to, and if you remember whose result that was, I mean, I would.
Yeah,
of course,
there is Physics Uspechy by Dotsenko. I think it was many years ago, some 20 years ago.
Okay, I will look it up.
It's about how small disorder changes the critical behavior. Yeah.
Okay. Very good. Thank you for that comment. And well, I guess I should come back to the question by Garabet. So yes, again about the critical exponents, right? So yes, when the system is critical, then the correlators, right? So let's just call it x, y, just for simplicity, right? When you're not critical, they go like this, right? They go like L psi, where L is the distance between x and y. And when you're critical, this breaks down, right? So what happens is that x, y starts being, you know, psi or L with some power. Well, let's just not call everything alpha. Well, some nu, right? So this is true, and this polynomiality is there whether alpha is 0 or not. So now there is another aspect to criticality, which is expressed in the heat capacity. So when this first thing takes place, right? So when in the first case, we know that C, the heat capacity density, right? So C over N is O1, right? I mean, it's proportional to a constant. I mean, it's, well, you know, it doesn't scale with N at all, right? Now, in the second case, C over n is either going to be logarithmic, and this is the alpha equals to 0, or it's going to be n with the positive power, which is alpha is larger than 0. And this alpha is the thing that comes out in a dependence of C as a function of t. Because when we look at C as a function of t, when t goes to t critical, C diverges, and alpha is 0 when it diverges logarithmically, and well, alpha is larger than 0 when it diverges polynomially. So this is the deal with the critical exponents. I hope this is clear now.
Yes, it is.